We'll now begin section 4.3, where we'll discuss how to locate the real zeros of the polynomial. We'll begin by discussing the rational zero theorem. The rational zero theorem says that if we have a polynomial with integer coefficients, then any rational zero of the function must be of the form p divided by q, where p is a factor of the constant term at the end of the polynomial, and q is a factor of the leading coefficient. So let's look at this in the context of an example. So f of x is equal to 2x to the third plus 5x squared minus 4x minus 3. And we want to identify all of the potential rational zeros. Then we want to write the polynomial in factored form and identify the actual zeros. So what we're going to do is we're going to identify two numbers inside the polynomial. One is the p and one is the q. And so the p-value is going to be the number that sits by itself at the end of the polynomial, assuming that it is in order from descending from the highest power to the lowest power. So our p-value is going to be -3. And our q-value is going to be the leading coefficient. So in this case, the q is going to be +2. And so what we want to do is we want to come up with the factors of both the p and the q. So if p is equal to -3, what are the factors? What two numbers could you multiply together to give you -3? We could multiply +1 times -3. We could multiply -1 times +3. And those are the only two ways in terms of using whole numbers that we can arrive at -3. And so we will say that our factors are, and I'm going to combine these, we have a +1 and a -1, so I'm going to write this +or-1. We have a negative and a +3, so I'm going to write this +or-3. Now we'll do the same thing for the q. Our q value is 2. So how can we multiply two numbers together to get 2? We can multiply 1 times 2, or we can multiply -1 times -2. And so again, combining these numbers, we're going to have +or-1, and then we also have positive or -2. And so what the potential rational zero theorem says is that if we have a zero for our function, then it must be of the form p divided by q. So we need to look at all possible ways to make fractions by putting a p-value on the top and a q-value on the bottom. So you want to do this somewhat systematically so that you don't end up skipping one by mistake. So I'm going to first take each of these p-values and put them over 1. So that would give me +or-1 over +or-1, and we'll reduce in just a second, and then +or-3 over +or-1. And then once that's done, I'm going to take the numbers and I'm going to put each of the p-values over the 2. So that would give me +or-1 over +or-2. And, well, wait, let me go in order. I apologize for that. So let's make this a 1. And then +or-3 over +or-2. Sorry, I had it right the first time, didn't I? We're putting them over 2. All right, so 1 over 2 and 3 over 2. And now we're going to reduce those fractions and get our final list. So our final list of p over q, we would have +or-1, that's 1 over 1. We would have 3 over 1, which is going to be 3. 1/2 and 3/2. Okay, and so our next slide should just confirm that we've done this correctly. Here are our factors of P. Here are our factors of Q. And here are our P divided by Q. All right, so again, potential rational zero theorem says that the zeros should be found in the list of numbers that we have for possibilities. So keep in mind that we have 8 possible numbers because we have the plus or minus on each of those 4 values. And so the next thing that we need to do, now that we have our list of potential rational zeros, is we need to try to identify which ones are actually zeros and which ones are not. And the way that we're going to do that is we're going to use synthetic division. So our book tells us to use synthetic division on a trial and error basis with the potential rational zeros. And so what this means is that we're going to take these numbers, the 1, the 3, the 1/2, and the 3/2, the -1, the -3, the -1/2, and the -3/2, and we're going to set up a synthetic division for each. The problem with that is that we have 8 numbers. And so we could conceivably be working this out 8 different times. And so using a trial and error approach may not be the quickest way to work the problem. So you may find, and this is perfectly okay if you want to do this, you may want to go back to your problem. You may want to use your calculator to get a quick graph of 2x cubed plus 5x squared minus 4x minus 3. And look and see where it looks like that graph crosses the x-axis, because remember that when we're talking about zeros, we're talking about x-intercepts. So if you want to do that, that will at least allow you to guess a little bit better and potentially prevent you from having to try all 8 of those numbers. Okay? So the book suggests that we try the 1 first, the positive 1. So we're going to go ahead and do that. If you are using your calculator, you should be able to see that it does appear that the graph crosses the x-axis at 1. So 1 would be a good thing to check. So we're going to check x is equal to 1. So we're going to put the 1 outside on our synthetic division. We're going to put the coefficients of our problem underneath. So remember, that means we're going to do a 2, a 5, a -4, and a -3. All right, so 2, 5, -4, and -3. And we'll drop the 2 down, and we'll multiply. 1 times 2 is 2, and we're going to add, which gives me 7. 1 times 7 is 7. We're going to add. That gives me 3. 1 times 3 is 3, and add, and that gives me 0. So if 1 is a 0, then the remainder should equal 0. And remember that your remainder is found right here. So if you work this out and you do not get a 0 at the end, then the number that you are checking is not a 0 and you want to move on to something else. All right, but we do know that x is equal to 1 is a 0 of the polynomial. All right, so let's look at what that leaves us. If I'm aiming to factor this polynomial, and I know that x is equal to 1 is a 0, what I know is that x minus 1 is a factor. Because if I plug this 1 in right here, I'm going to get 0. Okay, and then the rest of this factor form is going to come from what we have right here. So remember that if the original problem started with an x cubed, this starts with an x squared. So we have 2x squared plus 7x plus 3. Now, that is a first step in factoring, but it may not be completely factored. Note, however, that this is a quadratic with the highest power of 2. So it is possible that that quadratic would further factor. So let's check and see. To make 2x squared, we know we'd have to have a 2x and an x. To make the 3, we know we would have to have a 1 and a 3. And we need a positive 7. So we could make this positive and this positive and do a quick check to be sure. Outside would make 6, inside would make 1, added together would give us 7. So now we have this thing completely factored, which was part of what we were asked to find. Okay, we were also asked to find the list of potential rational zeros, which we did right here. So this is also part of our answer. And then we were asked to find the actual zeros. So we know that x is equal to 1 as a 0 based on our synthetic division. We also know that, and I'm going to have to work this out real quick. We also know that negative 1/2 is a 0 based on that 2x plus 1 factor. And we know that negative 3 is a 0 based on the x plus 3 factor. And that completes part A of our problem. Okay, so let's go back and let's do the other part. So part B gives us a little more of a complicated problem. Let me erase all this. All right, we're going to do the same kind of thing here. We're going to identify our P as the number that sits by itself, and our Q as the leading coefficient. So our problem is 27x to the 4th minus 9x cubed minus 33x squared minus x minus 4. We've identified the P value as negative 4 and the Q value as 27. So let's consider the factors of the P. So we know that P is negative 4. Let's write down the ways that we can multiply numbers together to give us 4, or negative 4. So I can do a 1 times negative 4. I can do 4 times negative 1. I can do 2 times negative 2. And so if we combine these, this is going to give me plus or minus 1, plus or minus 2, plus or minus 4. For the 27, we can do 1 times 27, negative 1 times negative 27, 3 times 9, negative 3 times negative 9, and that is all there. And so combining those, that gives me plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27. And then remember that your list of potentials is going to be found, or your possible zeros, by doing P over Q. So we're going to place each of these P values over 1. And I'm going to simplify as I go. So 1 over 1 is just going to be 1. 2 over 1 will be 2. 4 over 1 will be 4. All right, now we're going to take those and we're going to put them over 3. So that's going to give me 1/3, 2/3, and 4/3. All right, now we're going to take those numbers and put them over 9. So that's going to give me 1/9, 2/9, and 4/9. And then finally, we're going to take those numbers and put them over 27. So that's going to give me 1 over 27, 2 over 27, and 4 over 27. All right, so again, we're just going to kind of check this. All right, so we have the factors of P and the factors of Q, just like we came up with. We have our list of P over Q. Okay, just like what we wrote down on the previous slide. So now our job becomes to go in and check. So we have the potentials done here. That's part of what we're asked to find. The next thing we need to do is find the actual zeros and get it factored. Now, again, the best thing you can do here is use your calculator, graph your original function, and look and see what makes sense to check. All right, so one thing that makes sense, I think, to check would be maybe 4/3. Okay, so I'm going to check that one first. All right, and we'll go to the next screen and check it. So we're going to check x is equal to 4/3. Remember that if you check a number and the remainder is not 0, then you just simply need to check something else. All right, so I am going to divide 4/3 into my original function, which is going to look like 27, -9, -33, -1, and -4. So we're going to drop the 27. Now, you may find here, especially with this fraction, that your calculator makes life a little bit easier. So we're going to multiply 4/3 times 27. That's going to give me 36. And we're going to add it to -9. And it's going to give me 27 again. And 4/3 times 27 is going to again give me 36. Add and I'll get 3. 4/3 times 3 is going to give me 4. Add, I'll get 3. 4/3 times 3 is going to give me 4. Add, and I'll get 0. So because I got 0, I know now that x is equal to 4/3 is a 0 for your polynomial. Okay, so back glancing at the calculator again, let me see what else might be a good thing to check. And you might say, hey, let's check -1, because -1 looks like a good choice. So what we're going to do is we're going to set up our synthetic division using the -1. Now, you don't want to go back to the original problem with this because you've already reduced your polynomial one time and you've come up with this. So we actually want to use this first step here to do our synthetic division the second time. So I'm going to use these coefficients. We're going to drop down the 27. -1 times 27 is -27. Add and we get 0. -1 times 0 is 0. Add and we get 3. -1 times 3 is -3. Add and we get 0 again. So we can conclude that -1 is also a 0. Okay, one helpful point here to make is that if you go back to your original problem, you notice that the original problem, let me find it. Okay, the original problem has a 4th power on it, which tells us that when we're done, we should have 4 zeros. If you can do synthetic division and find 2 of the zeros, then you have now reduced your 4th power down to a 2nd power. Because keep in mind, when you put the x's back into this, if it starts with a 4th, this is a 3rd, and then this is a 2nd. If you can get your problem to a 2nd power quadratic, then you can solve it by either factoring or quadratic formula. So that should be your goal. If you have 4 zeros, find 2 by synthetic division. If you know you're going to have 5 zeros, then you want to find 3 by synthetic division. You want to reduce that polynomial to a quadratic if at all possible. All right, so let's look at what we've got here now that we have gotten to this point. All right, so I know that in terms of factoring this thing, I'm going to have a factor that looks like x minus 4/3. And I'm going to have a factor that looks like x plus 1. That's coming from these 2 zeros. And then I'm going to have whatever I'm left with here, which is, remember this is a squared term, so 27x squared plus 0x plus 3. Now we want to look at this 27x squared plus 3 and see if we can factor it. But as I start to look at it in terms of factoring, I see that I do have a common term. I could pull a 3 out. So I want to do that. I want to get rid of this 3 to make things just a little bit easier. So if I take a 3 out, 3 times 9 is going to give me 27, and 3 times 1 is going to give me the 3. Okay, so let's look at what we've got now. Okay, so I'm going to come off to the side somewhere, and I'm going to solve this 9x squared plus 1. So I'm going to move the 1 to the other side by subtracting it off. So 9x squared is equal to negative 1. Divide both sides by 9. I have x is equal to negative 1 over 9. And then take the square root of both sides, and I'm going to get x is equal to positive or negative I, and then the square root of 1 is 1, and the square root of 9 is 3. Okay, so now I can take, those are my other two zeros. Now I can take that, and let's finish up this factoring. So I have x minus 4/3. I have x plus 1. I have this 3 that's kind of hanging out. And now when I factored this 9x squared plus 1, it factored into two parentheses. One of them was going to look like x minus I over 3. And one of them is going to look like x plus I over 3. Now, just for the sake of making things a little bit easier, let's go ahead and distribute that 3 back through that parenthesis bracket so that we can get it in simplified form. So when I do that, all right, so I'm going to multiply the 3 times every term here. So 3 times x is going to be 3x. When I multiply it by 3 times I over 3, the 3's are going to cancel. So I have 3x minus I. On the second set, I'm going to have 3x plus I. Okay, and so fully factored is what we have right here. X minus 4/3 times x plus 1 times 3x minus I times 3x plus I. And what are our zeros? Our zeros are 4/3, negative 1, I over 3, and negative I over 3.